In this video, we will be talking about the symmetric equations of a line. The symmetric equations are the equivalent of the Cartesian equation of a line, but in 3D space. In 2D space, the Cartesian equation of a line is fairly straightforward. We have ax plus by plus c equals 0. And that is the equation of a line, where x and y are the coordinates of any point on our line, and a and b correspond to the coordinates of our direction vector, which is given by minus b, a. So as we can see, the Cartesian equation of a line in 2D is neat. We have x and y on the same side of the equation. Conversely, we will see that in 3D space, the symmetric equations of a line aren't as neat as the Cartesian equation, because there's a slight complication in 3D space to such an extent that we can't express x, y, and z on the same side of an equation. As always, to find the symmetric equations of a line, we need to start by the vector equation, which is given by our general position vector r, which is equal to a specific point on the line, which has a position vector a plus a parameter t multiplied by the direction vector u. Likewise to the Cartesian equation of a line. To derive the symmetric equation, we need to write each individual coordinate for our three vectors over here. So first we start with our direction vector u, which I will call a in the x direction, b in the y direction, and c in the z direction. And to avoid any confusion, I will, instead of having our vector a over here, I will call it r naught, to avoid any confusion with our coordinate a for the direction vector. As an aside, the reason why I bring up different forms of notations is because it's a very important skill to get accustomed to these varying notations, because you will see that people write in different ways. And so if you get accustomed to these different forms of writing, then it will be easier for you to understand what other people are writing. Going back to the subject, we now need to find the coordinates of our position vector r and our position vector r naught. And so our position vector r, we already know, since it's a general vector, we will consider its coordinates to be x, y, and z. And for r naught, we'll say that it's x naught, y naught, and z naught. So from our vector equation, we can write down a set of three equations. So we have x, which is equal to x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. And where does this set of equations come from? Well, we know that from our vector equation, the x component of our vector r will be equal to the x component of our vector r naught plus t times the x component of our direction vector u. In other words, x will be equal to x naught plus t times our coordinate a. And that's where this equation comes from. And likewise for the two other equations. What's key here is that if we make t the subject of our three equations, we first get that t is equal to x minus x naught divided by a, and this comes from our first equation. But it also equals to y minus y naught divided by b, and finally we have z minus z naught divided by c. And these are what are called the symmetric equations of our line. And contrary to the Cartesian equation of a line, we can see that it would be messy if we try to express z as a function of y and x. And that's why, compared to the Cartesian equation of a line, it's not quite as neat. In other words, we don't have something equals to 0, as we would have had for the Cartesian equation. Now, what I want to do here is give a bit of terminology. So this set of equations, these equations are called the parametric equations. And the reason why they're called the parametric equations is because these equations feature the parameter t. And remember, the parameter t is just a scalar. And this right here is corresponds to the symmetric equations of a line. Now, I want to emphasize something really important. What if one of the coordinates of our direction vector u is 0? So for example, our coordinate c here is 0. So we know that we can't divide by 0, and therefore we need to figure out what we need to do. Note that from our parametric equation over here, if c was 0, then we would have z equals z naught. And therefore what this means is that our symmetric equations would therefore be in the form x minus x naught divided by a equals y minus y naught divided by b, and finally we would have z equals to z naught. But they would not be in the same equation. One final point I want to make is explaining and clarifying why the symmetric equations, why their form makes sense. So from our vector equation over here, we can rewrite it as r minus r naught equals tu. And r minus r naught, it's the difference of these two vectors is also a vector. So essentially what we have is a vector d that is equal to t u, t times the vector u. And therefore these two vectors are equal to within t. In other words, they are parallel. And we know that if two vectors are parallel, then their components are proportional. And since the coordinates are proportional, we essentially have these three ratios over here that are equal to each other. And that's why the symmetric equations make sense from a conceptual standpoint. Thank you for watching this video. If you have any questions, leave a comment down below. And if you enjoyed it, don't hesitate to drop the like button.